Tommy, thanks for being here.
All right, well, we'll go ahead and get started. So good evening. My name is Katie Malinowski, and I'm the Executive Director of the Tug Hill Commission up in Watertown. For those of you who may not know, the Tug Hill region covers 2,100 square miles in Jefferson, Lewis, Oneida, and Oswego counties. We're a small non-regulatory New York State agency that helps the towns and villages on Tug Hill in the areas of land use, planning, local governance, community and economic development, and natural resources planning. We also host and plan conferences and workshops like tonight to help our communities build capacity, create historical presentations by community request, and sometimes we present or have people come in and present on relevant cutting edge topics. So tonight we have Scott Steiger, Professor of Meteorology at SUNY Oswego and the Director of the Lake-Effect Storm Prediction and Research Center. We've known him for several years now. First, he was one of the investigators for the OWLS project several years ago, which stood for Ontario Winter Lake Effect Systems, studying the lake effect snow phenomenon several years ago. And more recently at SUNY Oswego and several other partner universities secured a $1.3 million grant from the National Science Foundation to study lightning and lake effect storms off Lake Ontario. The commission was able to play a small part in that most recent research by helping find some of the volunteer landowners and tracking down weather balloons once they landed. And we're gonna, I think, see some a visual here tonight of some of that. So thank you to all the local landowners who participated, who volunteered their properties for the lightning mapping arrays. It was a lot of fun, and I'm excited to hear tonight's presentation. So he's going to go over some of the initial findings from last winter, as well as some of the storm chasing stories in Tug Hill by his team. Everybody loves a good storm chasing story. So before I hand things off to Scott, I would like to make note of a few housekeeping items. For this webinar, we've got people online. Attendees are muted unless at the end we decide to unmute them and let them ask some questions. We also have one of Scott's students on who's going to share some of his experience with us. Any questions in the room, obviously raise your hands. Online, please type them into the chat box. And we are recording the webinar for later upload to the Tug Hill Commission's YouTube channel, so you can watch it later or share it with anyone that might be interested. And we'll send you links to that recording and follow-up emails. So with that, I'll turn it over to Scott.
Thank you, Katie.
Thank you.
Thank you. Thank you, Katie. Thank you, Taylor. Thank you, the Tug Hill Commission overall, for having me and welcoming me to talk to you all this evening about a pretty exciting project we had last year called the Lake-Effect Electrification project. What you see in the background here is the only photograph of a lightning strike in a lake-effect snowstorm I've ever seen. This was taken by one of my students, Caitlin Jesmond. You can see she got just the clip of it as it's hitting one of the towers in Oswego, one of the smokestacks. So we were really excited that day, and this is one of the days we were out there doing research. So also I would like to recognize Thomas White. He's one of my students. He's going to share some of his experiences during the project. We had over 20 undergraduate students participate in this project, out in the field, launching big weather balloons, running a Doppler on wheels radar truck, collecting snowfall measurements. So we'll talk about that and some of the safety issues that go along with that. But yeah, this is a really scientifically interesting problem, how we get lightning when all the precipitation is frozen. Most of the time we get lightning in the summertime, right? When we have a mixture of frozen particles upstairs in the clouds, but then it transitions to rain to the ground. Please, I'm very casual about how I present, so if you have any questions in the room or online, you can interrupt me anytime. If I show something like, what is that? And I didn't explain it well, please stop me. So Katie, I guess we'll go to the next slide, please. I'd like to, are you connected to the internet? I should have asked beforehand.
We are, but we'll see if the video.
Maybe click on the YouTube, we'll see if it happens. Okay. And, oh wait, not that one. Well, we can play that one, that's fine. That's fine.
I don't know how that's going to work for the people online. They might not be able to see the new screen.
Yeah, then let's just show that video that we have there. Yeah.
Somebody's very excited on YouTube.
That was Jim Cantori from the Weather Channel, jumping in joy as lightning and snow happen. This is probably one of the most exciting things for meteorologists, maybe humans in general, to experience when it's a blinding blizzard and you experience lightning. So why don't you go ahead and play that video? This is one I actually took from the roof of the building in Oswego. You can see I wasn't as animated as Jim Cantori. Why don't you play it again, please, just so we can see that. This was just last year on the roof of our building, our science building. So yeah, it was kind of exciting. Sorry, I swear when get a little excited. Any of you in the room seen thunder snow before? Right, so several of you have. Right, this is one of the top spots in the world, behind Japan, believe it or not, that gets lightning in snowstorms. East of Lake Ontario. You live in a very unique area for many reasons, including all the heavy snow we get, but also the electrification of these storms. Next slide, please. Oh yeah, it plays it. Yeah. So just a little bit background on lightning, just in case no one's taken a meteorology course before. Basically, what's going on in a thunderstorm is that you have particles of different phases, what we call in meteorology. There's ice, there's liquid water, there's snowflakes, and even in a summertime thunderstorm, because they grow so deep, up to like 10 miles above the surface, where it's really cold in the summertime still. And as you get an updraft and downdraft, these particles kind of rub up against each other and separate electrical charge. And the grapple, which is like small hail, right? You probably experienced that in Lake-Effect snow, like ice pellets. We call that grapple, right? They carry negative charge, and because grapple particles are heavier, they fall to the bottom of the cloud, toward the bottom of the cloud, and then the snowflakes get more positive charge and are carried upward because they're lighter. So that separates charge, negative, positive, and then there's some negative and positive down closer to the ground as well, due to things going on with a tree I can talk about maybe later. But that separation of electrical charge increases electric field to a point where electrical breakdown happens. And that's what's called lightning. And the same thing happens when you're dragging your feet along a rug on a cold winter day and touch a metal doorknob. Everyone gets zapped by doing that? It's a pretty simple process, what's going on, but it's very complicated. The devil's in the details about how to get enough charge separation to get lightning. But essentially, that's the basic premise. It's basically charging a battery is what's going on. However, this is like a summertime storm. During the winter, just make this a lot shorter and much closer to the ground. And there's some different unique processes going on during the winter compared to the summer. Next slide, please. So why east of Lake Ontario to study wintertime lightning? Well, number one, as all of you know, this is a hot spot for snowfall in the whole country. Okay, east of the Rocky Mountains, you live in one of the snowiest, probably the snowiest, if not the second snowiest area east of the Rocky Mountains. The Rocky Mountains are off the charts. There's some places in the Rocky Mountains that get 1,000 inches per year of snow, right? People don't live up there, right? They're like resorts and they shut down. Ever see The Shining, right? That's kind of the basis there. East of east of the Rocky Mountains, kind of closer to sea level, not in tall mountains, we're tied kind of with the UP of Michigan, the Upper Peninsula of Michigan, in terms of the most snow per year. Generally, kind of near where you live, Redfield, I know there's a lot of bragging rights here in the Tug Hill, but Redfield, our research has shown, is the hot spot. They average over 300 inches per year. Where I'm from, here in Oswego, we average closer to 140. And where I grew up here near Rochester, we averaged like 100. So growing up near Rochester, I heard of this mythical place known as Oswego that gets all this snow. And to be honest with you, that's the reason why I went to study there as an undergraduate and came back as a professor. And I think a lot of the students who are, if they're online, would agree that's why they came to Oswego, even though they've been very disappointed the last 5-6 years because our snowfall has dropped tremendously. Like I said, we average 140 per year. Now we're averaging closer to 50 to 60 inches per year the last 5 years. It is not the same Oswego that many people heard about. Like on the Johnny Carson show in the 60s, we were famous because we got all this snow and we're on Johnny Carson, right? There's a clip somewhere on the internet where you can find that. So next slide, please. So what about lightning and snow? Well, generally speaking, the reason why we get more lightning in lake-effect snow as opposed to other snowstorms is that the lake, think of the lake during the wintertime as essentially a boiler. It is so much hotter than the air above that it creates very turbulent, violent in a way, motions, up and down motions. And you have all this water vapor coming off of this hot lake. Think of the steam coming off when you're boiling water on your stovetop. You have all this steam coming off and violent up and down motions liquid water, snowflakes, all that grapple that I showed with a summertime thunderstorm exists in lake effect because of this. Basically, it's a hot plate. Lake Ontario is effectively a hot plate during the wintertime. I mean, the temperatures, let's say near 40, 45 degrees Fahrenheit, November, December, lake surface temperatures 40, 45, and the air above is, closer to 10 or 0 degree Fahrenheit, let's say a mile above that lake. So it really gets these turbulent motions. So we've known this for a while, for decades, that you get lightning and lake effects. So we want to do a climatological study to show where most of the lake effect lightning happens. So you can see it's mainly over the lake of Lakes Erie and Lake Ontario. Maybe the lightning goes in a little bit, 10 miles or so, but it's really tied, we found, in the period 1995-2007. Most of the lightning happened over the lake and maybe right near the shoreline. Next slide, please. We did that study that Katie mentioned called the OWLS project 10 years ago, Ontario Winter Lake Effect Systems Project. And we notice each of these dots, green or red dots, represent a lightning flash. This is for one event, right? You'll notice none of the lightning happened over the lake. Right? Now, the OWLS project was in 2013-14. That previous climatological study only went up to 2007. Something changed in your terrain on the Tug Hill between 2007 and 2013, and it's not natural. What do you think it was that changed? A bunch of wind turbines went up, right? So I hypothesized for this project last winter when we proposed it to the National Science Foundation that the turbines changed the lightning climatology of the area, mainly during the winter. See, during the winter, cloud bases are a lot lower, right? And you have these, 300-foot turbines rotating and literally entering, leaving the clouds, right? That's like poking the bear, right? That doesn't happen during the summer because the cloud bases are a lot higher above the ground. During the winter, they're a lot closer to the ground. So they're poking the bear, enhancing the electric field in that lower part of the cloud, initiating lightning. That's what our hypothesis was. And we tried to show that and get data last winter to support that idea. So generally, now compared to summer thunderstorms, right? These are low flash rate storms. We're talking 5-10 flashes for over several hours, right? During the summer, we can get 5-10 flashes in 5 minutes, right? Or less. So these are low flash rate storms. So these storms are unique in that they represent kind of the bare minimum we need to get lightning in terms of what's going on in the clouds. So that's another reason why the federal government was very interested in studying these storms, because scientifically, it's kind of very unique. And lake effect bands last for hours, as you know, so it gives us plenty of time to study the storm without it moving much, right? It's kind of tied to the lake, so it's relatively easy to study compared to any other snowstorms or even summer thunderstorms, right? So any questions so far?
What are the stars? The villages or the blue stars?
So very, very good. One of the stars should be Sandy Creek. I think this is Sandy Creek right here. This is where we had a lot of instruments set up in this array, right? So as we went up the tug, we could measure how the band changed. So yeah, and then the triangle, the square, those are also other instruments that were deployed during the project. But the dots are the lightning. The red represents intercloud lightning, just lightning that stays in the cloud, and the green shows cloud to ground lightning, that hits the ground. Most lightning typically stays up in the cloud; it doesn't hit the ground. But we think that's changed ever since the turbines were put up. Anything else? Anything online?
There was one, Kelly Campbell, did you have a question? Let's see if I can let Kelly talk. Kelly, you should be able to talk if you want to ask your question. Maybe not.
Looks like he's connecting to audio. He might be having.
Okay. Thanks, Katie.
Okay. Well, we'll certainly have time for questions later. We'll keep track of the time because I definitely want to at least let Tommy talk a little bit about his experiences during the project.
Very good.
So yeah, that's kind of the background so far about leading up to this project. Next, please. Now, this is an updated lake effect lightning density, including time after the turbines were put up. The turbines were put up in 2006, 2007. This is 2011, 2021. Still a lot of lightning over the lake, but you'll notice this maximum lightning activity right here. Those are the turbines. So we're seeing it without even any fancy equipment. Just there's a operational network of lightning detection systems around the world right now, around the country and so forth. So It's not really high-res lightning data, as what I'm going to show you in a little bit, but it still shows a decent signal, right, with those turbines. It was not there before 2007. Next, please. I'm not going to read this to you, but the main objective really was we don't have any idea how electricity is generated in lake-effect snowstorms. We know that lightning happens, but how does the charge get separated? Where are the positive charge regions? Where are the negative charge regions? Is it tied to snowfall rate? Is it tied to where this hail graupel particles are? Right? We just have no idea. So as a truly scientific question, this is like discovery, right? What is going on, right, in these clouds electrically? We do want to improve our understanding of how turbine-initiated lightning happens, because once turbines get hit by lightning, they do have lightning protection equipment on them, but sometimes lightning is so powerful it still blows up the turbine, right? And costs quite a bit of money to replace those turbines. The other thing too is if turbines are initiating more lightning, we need to know that to help protect the public, right? Before we start putting turbines up, we obviously don't want them in a highly populated area. And if people are living near them, we want them to be aware of potential dangers of this kind of lightning. And then compare the findings with other kinds of winter storms, for example, in Japan. Sometimes in nor'easters, you can get lightning, so I compare and contrast with that. But one of my key objectives, too, is involving undergraduate students, right? Most of this kind of research is done by grad students or other scientists. So it just made me so excited and happy to involve undergraduate students, freshmen, people who just the year before were in high school, were out there launching and playing with $1 million pieces of equipment. It was cool, right? It was, now they were supervised, right? We just didn't have them drive the Doppler on wheels just by themselves. But it was really cool as an educator to see my students out there in the field. Some nights were long, right? They have to stay out. There was one event they stayed out for 14 hours. That was a long event. So I was really grateful to their hard work and dedication. Next, please. So what kind of instruments did we set up? Well, we set up an array of essentially complicated AM radio sensors, right? Ever listen to AM radio? Maybe the younger folk haven't ever listened to AM radio, but AM radio is very sensitive to when lightning happens. You can hear the static, right? So essentially, we developed these instruments that listen for the static from lightning, and by using sophisticated mathematical modeling and so forth, you can, if you will, triangulate where the lightning is happening, so we can detect the lightning, right? So we set up sensors that, now these aren't the exact locations, but just to give you an idea, we set up 16 of these sensors on people's properties. One of them was across the street from Katie's house. And I thank the Tug Hill Commission. They work so well with us to work with the community, work with some of the neighbors and so forth to put these essentially just expensive radio receivers, on their lawns, right? We also had a radar truck. You'll see a picture of that shortly, right? That's the most expensive vehicle I've ever driven, right? Costs over $1 million to build. So I'll never drive a Lamborghini probably, but this was more expensive than a Lamborghini. So that was cool. And then the purple or pink, because I'm colorblind, those are where we launch balloons, right? And these are big balloons. You'll see some video in a little bit that are used to measure the electric field as they're going through the clouds, temperature, humidity, wind, all that kind of neat stuff. To launch one of those balloons, it took 8 people to launch one of these balloons at a time. That's how big they were. And hard to launch. I mean, you're dealing in blizzard conditions, right? That's extremely crazy, situations to launch a balloon into the sky. So next, please. So yeah, this is what the lightning mapping array sensor looks like. So there were 16 of these around the Tug Hill, right? You can see here it was last September when we were installing one. I think this is at Sandy Creek High School. Oh, sorry, Pulaski. Ooh, boy, I hope I didn't get someone mad. All right, Pulaski, thank you. And then we had, this is a one in the snow. This was one of the problems, and we knew this going into this project, the solar panels, right, because we don't connect these to electricity. Everything's solar paneled, solar powered, that they get covered by snow. So literally part of the students' jobs, I paid them to go out and brush snow off of the solar panels, right? Because we needed the batteries to get charged. And then this antenna here is essentially what's listening for the lightning, right? And it has to be a certain length and certain configuration, because lightning radiation is at a certain wavelength that the antenna can detect. Next, please. Here's the Doppler on wheels, right? So maybe some of you saw this and didn't see this around last year. Yeah, you saw it driving around, right? So basically it's a weather radar. The Tug Hill is not great to go around with a radar because you have so many darn trees. But 177, right? The west-east corridor, right, where the turbines are kind of, that's where this is pretty good visibility in terms of with trees, not with the snow in that picture. We had to go out ahead of time and like plow out sides of roads. We made inroads with some of the community members to have pre-positioned places we could send the Doppler wheels to like park in their parking lot, or I think one of them was a bar, but no one had a drink until after the project that day was over. So yeah, I mean, and once we have the radar rolling, it's pretty just runs on its own, right? We tell it where to scan. Generally, the radar was scanning, doing vertical cross sections through Lake-Effect snowband, and then also scanning around on the horizontal. Next, please. And then this is kind of like our armada of trucks that would go out. Anyone see these out in the field last year? These trucks, essentially, these are masts having thermometers and hygrometers measuring humidity, wind speed, wind direction as we're driving through the band. The U-Haul trucks, that's where we filled the balloons. That's to give you an idea. That's how big the balloons were. Because to fill the balloon out in the snow and 50-mile-per-hour winds, that would be really hard. So we filled them up in these U-Haul trucks, 26-foot U-Haul trucks. So we had to rent 2 of them each event. Next, please. And like I said there too, most of this stuff happened at night. Lake effect snow intensifies at night. That's when it's most intense, especially right before sunrise. So this is why it plays havoc with superintendents, because right before sunrise, the lake effect bands are the most intense, because that's when it's the coldest out. So you get the most instability over the lake to make the band the strongest. So yeah, right when they want to send the buses out, that's usually when it's the worst. So unfortunately. So here's an example of the sound. Look at this side. This is a balloon, one of the other balloons covered by a tarp to keep it protected until we were ready for it to be launched. You'll see a video of that shortly. And then attached to it is what's known as electric field meter. And as it goes up, this thing is rotating on a horizontal axis, rotating on a vertical axis, and it's getting all the components of the electric field as it's going up, so we can see how the cloud is getting charged. Remember the battery analogy, how it's getting charged. We wanted to see how quickly it was getting charged and how strongly inside the cloud is getting charged. To fill one of these balloons, this is not a normal National Weather Service balloon. This is much larger. 2 big helium tanks, right? And each helium tank was what, $300? So we had some problems where the balloon burst sometimes, right? Poof, $600 up in the air. Because helium got really expensive the last couple of years.
Where'd you get those?
The helium?
Yeah.
Air Gas. Air Gas is a company, national company that supplies different gases. Just to give you an idea, we budgeted $16,000 for all the helium we needed for the project. By the time we got to order the helium, it went up to $22,000. So really expensive to do research, but well worth it for both educational and the research. But yeah, and we had to get these instruments back, right? So there was a tracker on them, and they would land in middle of yards, on roads, in the middle of fields. So we had to go recover them. So I'll show you some pictures and some of the challenges with that in a little bit. Students also, while they were out, would collect snowfall measurements, like how quickly the snow was piling up on snowboards. They would take pictures of the snowflakes on black cloth to get a sense of what the kind of crystals there were. Not every snowflake's the same. You can get the Charlie Brown snowflakes, those big snowflakes, or you get the pellets, right? So we wanted to measure that and keep track of that so we could relate it to lightning, when lightning happened. Any questions? Okay, next slide, please. This was a really neat event that produced, this is what we call grapple. And you'll notice the grapple kind of looks like, I hate to use this analogy, but a bullet. Essentially, they form like a pyramid, right? Because the way grapple forms is as an ice particle is falling through the cloud, it collects water, supercooled water on the bottom, and that freezes on the bottom, and it just gets bigger from the bottom, right? So that's why it winds up looking like a pyramid. This was the largest grapple, which is this is the initial formation of hail in the clouds. This is the biggest grapple I've ever seen in my life. I mean, it's like 3/4 inch, and it was blowing at us at 50 miles per hour during this event. This was November 20th last year. That we tried to launch 3 different balloons. Those balloons I just showed you, each one of them popped, because essentially these were 50-mile-per-hour bullets hitting the balloon. So, and that was a great event. That's the event that I got the picture of Caitlin got the picture of lightning in the stack in Oswego. We couldn't launch one balloon in the whole project because it kept popping. So field work is really challenging. Here's a video showing you, if you listen carefully, you can hear the grapple hitting the window. Now it's kind of hard to, maybe online you can hear it. Hear it a little bit. But that's essentially these things hitting the window at SUNY Oswego, one of the buildings we're in at SUNY Oswego. There you can see the pictures of it bouncing, right? There, you know, so it's definitely not a snowflake. It's kind of an ice particle. And here's a picture from the back of the van showing how we're filling the balloon, how you can see how we fill the balloon. It's in a tarp, like a pool cover, and we drag it out of the truck, and then we bring it out to a field. And then, well, you'll see the video. Someone rips a line and it opens and there goes the balloon. So I'll show you a video of that in a little bit. Next, please. Yeah, it does that. It starts the video over again. Sorry. We also launched radio sondes that measure temperature, humidity, and wind in the vertical using a regular weather service balloon, size balloon. We did that outside the bands at SUNY Oswego. Part of the problem on our roof is that it was so windy and the wind accelerated as it's going over the roof that this thing kept tipping over. One of the events that tried to tip over, it almost tipped over this railing onto cars below. So, I mean, doing this kind of research in hazardous weather is tough. You know, I've tornado chased, I've done tornado research and so forth in the middle of the country. I don't feel my life is in much danger in Lake-Effect weather, but it is. And if you're smart with, you know, studying a tornado, you can stay far enough away, know where it is. But there are certainly challenges that were unique to studying in snowstorms, Lake-Effect snowstorms, and because of the high wind and low visibility. Next, please. So this is one of the challenges of those big weather balloons we launched, going back to the big weather balloons. There's where one of our sensors landed, way up in a tree. So we literally had, thanks to Katie and others on the Tug Hill Commission, we got contacts to tree climbers and so forth that would go up and get this. We'd go out in snowmobiles into the middle of the forest to find these things. I didn't personally, but one of the people from Oklahoma were part of the project. He was just loving it because he told me in November, I want to see a multi-foot snowstorm. I've never seen that much snow. He saw it up in Watertown, near Watertown. They had two big events last November into December. So he got to see the deep snow. One of the problems why the balloons kept popping, we realized, is that pool cover-like material, in the cold air, it would get really rigid, and the balloon, it would scrape the balloon. We believe that led to it popping the balloon. So what we did to solve that problem was kept them warm in a room, and then when we took them out in the field, we kept them in the car to keep them warm until we really needed them. And that helped to alleviate the problem of those balloons popping. Of course, that large bullet grapple hitting at 50 miles, there's no way to solve that. I mean, the only way to solve it is get a much better balloon, but they're a lot more expensive. But okay, I didn't drop something. They're a lot more expensive, so we didn't have time to get them for the project. We are thinking of doing a Lee 2 in 2 summers from now, because we did have a lot of issues with some of the equipment that we want to retry it, at least for maybe a week or 10-day period when it's really active up here, probably in 2 winters from now. So maybe in touch, needing some more help again in a couple of years. So next, please. Here's a video of us launching one. So yeah, you can just play that. And there it goes. There's that word again. But it detached, unfortunately. And it uses, we use really powerful fishing line, right, to connect things. But still, because it was so cold, the fishing line got brittle, I think, and it snapped, right? So if anything, this was a great experience. I know there's a lot of failures, right? But by failing, you learn, right? And that's what we did, and that's why we're hoping to do a Lee 2 in a couple of years, because we've learned a lot about how to solve that problem. Next, please. Yeah. In the deep snow, we had our snowshoes. Our friends, some of the scientists that were involved with the project were like from Texas and Oklahoma, because studying lightning, that's where most of the scientists are. They study summertime thunderstorms. So they came up here and they were like, oh God, what are we gonna, we got snowshoes. We'd go out in deep snow and collect our instruments. Sometimes though, they got buried and that was hard to find them. We had to really, that took a while to find some of the instruments, but we did recover every instrument that we launched in a balloon. It generally would go up about maybe a mile or so, because once it got above, maybe 2 miles, once it got above the lake effect band, we got all the interesting data. And remotely, we had a way to cut the line and let it sink. The instrument sink down on a parachute. So that was cool. The balloon eventually would go up high, and then pop, and then all the helium would go, and there we go. So as I tell my students, it's a cost-benefit analysis. You can't, I mean, the benefit of getting all that data outweighs the cost of the helium and the little pollution, right? I mean, a latex balloon, this big latex balloon's landing somewhere, and we're not recovering that. But it's that cost-benefit analysis. So next, please. Hi. Yeah, that was kind of the operations center. That's my office, and I slept in that chair a few nights. I mean, I only live a 15-minute walk from home, from my building to my home, but I was up there till midnight with leading forecast discussions or working with the students, getting ready, and then I had to get up at 4 a.m. to tell the Doppler and Wheels radar truck where to go. So instead of going home for like 2 hours or 3 hours of sleep and bothering my wife in bed, I just slept in my office. So, but compared to what some of my students had to deal with, that was very cozy, because some of my students, like, as Tommy will tell you about, it was rough. They had to sit in cars for, like I said, 10 hours in a row, and they made some fun. They made like balls to kick around, balls of snow to kick around. So when we weren't doing anything. So, but yeah, it was fun. Next, please. So a little bit about last year's winter. It kind of was really interesting in that we got the best events that we were looking for were our first events. Generally, when you're running a project, you don't want your best events to be your first events, because you're still working out the kinks. We still got great data, but it really was. These were I called them these were Super Bowl events. Mid-November, November 18th, 19th, and 20th last year. I don't know if you remember, but like Watertown area, just north of the northern Tug, got pounded by Lake-Effect snowstorms. And as the band sank south and went over the turbines, they lit up like a Christmas tree. I mean, you just see flash almost every minute for a while. Boom, 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 boom. And it was really amazing event. But because we're new at, we missed collecting some data, right? We didn't go out that night that it lit up like a Christmas tree. We got the lightning data, but we don't have any Doppler on Wheels radar data, because some of the scientists, I think, were nervous about being out at night. They didn't believe me that we had to go out at night. They're used to studying thunderstorms where, at nighttime they start dying. No, well, not Lake-Effect snow. So unfortunately, we got great data, but there were some kinks that got worked out. But they were great events still. And then, the big snowstorm happened in December. We missed that because Santa Claus came to town and all my scientists went home, right? I can't make them work on Christmas, all right? So we missed collecting some really good data those couple days before Christmas. There was another big event. Yes?
My daughters live in West Carthage and they got 5 feet of snow.
Yeah.
One got 5 and just about a mile away. The other one got like 2 feet.
Yeah.
That much difference,
Yeah.
And I remember I'm just south of there by about 10 miles, and I've never had so many thunder snows in a short period of time, like you're talking about. I mean, we had 6 or 7 within like 20 or 25 minutes a couple times.
Wow.
Just like, it's just snowing like crazy, just lighting up.
Yeah.
It's really neat.
Yeah. No, I don't think without those turbines, it wouldn't have happened as much.
Yeah.
Yeah. Those turbines they really changed things. Next, please. We'll skip this because I know we're running out of time. I want to make sure students, but yeah, it's a video showing just how bad it was, right? But you guys know how bad it is. Like I've shown this kind of video around the country, right? But you all know what snow looks like up here. So overview of some key results. This is what's plotted here is a lightning density map of all the lightning that happened in wintertime precipitation and frozen precipitation last November through February, right? And you can see the hot spot is right where those turbines are, right? Those are the center points of the 3 turbine fields that we have information for. There was an event in Canada that was associated with wind turbines in Canada. And then there's the event that hit Oswego, that Oswego tower that I showed you a picture of. But you can see most of the lightning was associated with those turbines. Once again, not a lot of lightning out over the lake. right? We recorded data on almost 240 flashes in that November to February period during, snowfall, when ice was falling. The maximum flash rate was about 26 per hour, right? For a wintertime storm, that's pretty intense, right? 26 per hour. And a lot of the flashes, especially during this event, we call them IOPs, intensive observation periods. This IOP3, which was November 20th, over half the lightning was within 300 meters. It initiated within 300 meters of a turbine. So probably was initiated by the turbine, right? Probably by a turbine. Yep. So it's really good data. We'll skip ahead here. Next slide, please, Katie. I'm going to skip this slide. We'll go to the next slide, please, just because of time. I just want to show you this this is how we look at the lightning data. And I want you to think each of these dots you see here is a piece of a lightning flash. This is one lightning flash. This is time versus height, right? And this is like a quarter of a second in time. And you can see how the lightning initiated off a turbine, went up, and then jumped up, down, then jumped back up, down. Why it does that, I could talk with you later about that, but it's called a bi-level flash. And you can see, and this is the plan view. Here's Lowville, right? Each of these blue things is a wind turbine, right? So we can track it to where it was initiated. See the purples when it started, track it to a specific turbine. And then you can watch how it spikes. See how it's kind of, lightning branches? You can see it branching like this, right? And branching up here, right? So pretty neat data. It's just fascinating that you can map out just one flash in that much detail and see how it originated near a turbine. And there's the radar data at the time. So this is when a band was right over, like the Montague radar, right over the turbines. This is a vertical cross section looking through the storm from the Doppler on wheels radar truck. And you can see how, it's about 5 kilometers tall, which is about 3 miles, 3-4 miles tall of a lake effect snow band. So really, really neat data. Any questions on what I'm showing here? Because it's kind of complicated. But
There's one online if you have a minute.
Sure.
Sure. Tom and Audrey want to know, do the turbines close to Lowville have an effect on lightning strikes on the western Tug Hill?
On the western Tug Hill, I don't know. This is focused on the eastern part of the Tug Hill, right? That's where the turbines are. But how it affected lightning upwind, we're still just starting to delve into these data. So that's a good question, and hope to have an answer in the next few years. There's just so much data. I mean, it's the field experiment is the fun part, I think, the funnest part. And then analyzing data is fun, but not as fun as going out and chasing storms. But we got money for the next 3 years to pay students and myself to analyze the data, do presentations at science conferences, publish the data in journals and so forth. So, well, maybe I come back next year or, let you know what we find. This is just very preliminary stuff.
Thank you.
Yeah, thank you. Next slide, please. And then this is what's really one of my, this is so fun for me, to have a picture of a lightning hitting the stack. This is a physical picture, and there's the data. Each dot represents a piece of this lightning flash as it's going and hitting the tower and then moving through the band. Right? This is radar reflectivity. It's kind of blocky because there's like trees blocking the view of the radar, but you can see we got good radar data here, and you can see how the lightning propagated after it hit the turbine. Not the turbine. This is the smokestack. If you ever come to Oswego, right, you see the two Huey, Dewey, Louie, whatever the hell they're called, right? The stacks, right? And it got hit by lightning. So I got to thank Caitlin Jesmont again for taking that picture. Serendipitously. It's not like she planned. She just had her camera out the window, and it fell down, and then she put it back up just in time to catch the lightning. So it was great. She might even be online. We'll have to see if she's there. Next, please. So yeah, more pictures of the grapple. Next, please. So in conclusion, we had 11 events, 3 with lightning. And based on the climatology, that worked out pretty well. We had 7, based on the climatology, we had 7 planned events we were going to study with 3 with lightning. Well, we got 11, 3 with lightning. So that was pretty good, even for a relatively weak winter. It was a weak winter generally for everyone east and southeast of Lake Ontario. But if you were northeast of Lake Ontario, it was above average year for snowfall. Whenever Buffalo makes the headlines for big snowstorms, which they did last year, Watertown generally gets hit pretty hard, but since Watertown's much lower in population and they don't have a professional football team, well, we think they're a professional football team. After last night, I think they're a JV college football team. But anyway, you know, because they're a much bigger town, right? They get the press. So we did get some great data, lightning mapping array, lightning data during Lake-Effect rain events, right? Earlier in the fall, last fall. There's actually an event that produced flooding rains in Oswego where we got some good lightning data out of that Lake-Effect event. We're on Twitter. We have a website. You know, this will all be online, so you can take a look at it later. And then to conclude, I just want to show a video. I want to show Caitlin Jesmont's video of that lightning flash in slow motion. So we'll show this a couple times, please, Katie. You can see it. And look how it dances around the top of the stack. So there's a metal ring at the top of the stack. I think the electricity is from the lightning's dancing around. So yes, please, please. Really cool. Like I said, I mean, I've experienced Lake-Effect lightning many times in my life and thunder snow many times in my life. I've never seen the actual bolt, right? Because normally it's too snowy, you can't see it, right? So, and then who's going to have a video camera out during a snowstorm, right? So I love this video and the pictures from this. So I guess I'd like to switch it over to Tommy White, one of my students. Tommy, do you want to share a few words maybe on what it was like being out there collecting data?
Yeah, I'll share a few words. So it was a crazy experience overall. You know, coming into it, I just finished my first year, so I was a sophomore. And I was still, you know, taking some pretty beginner level classes. And I remember seeing the Mesonet, the mobile Mesonet, come into town, and I was like, wait a minute, like I'm learning about that right now. So I thought that was a cool experience. And then later on, I've also seen the Dow in Oswego, and I was like, oh my God, these things that I'm seeing in textbooks and online and I'm learning about in my classes, I'm like, I mean, wow, I'm gonna be working with them, you know, after I found out that I got the position. Some notable moments was IOP2 was the Super Bowl event Dr. Steiger talks about. That event I was in the Dow for, actually. I got to be one of the 2 students in Watertown, specifically CART, the airport, when that event was taking place. Now, if I was presenting, I'd show you a video of me and Michael Paganelli, who was another student, of driving to CART on 81, and it was whiteout conditions. It was so crazy amount of snow, maybe 3 inches per hour. You couldn't see more than maybe like a quarter mile, you know, out the windshield. And then the same day, I remember seeing at least 5 flashes of, you know, lightning, and that was my first experience with lightning as well. So I'm getting a lot of firsts with the project. You know, and the project also has opened me up to, like, you know, the good and the bad, you know, sides of you know, data, you know, gathering data. You know, specifically, like it's kind of hard to forecast these Lake-Effect bands, and so sometimes, for example, we were out for 14 hours through the night. I think 10 p.m. or it might have been like 8 p.m. to 10 a.m. And a lot of the time we were waiting. We were just waiting for for a band to come over our you know, domain, our small little area. And that only happened about one time. I think it must have been 8 a.m. We were able to get EFMs up. We were able to see some significant snow. We were in the Lake-Effect band. But it was tough. It was tough waiting out, you know, all in the freezing cold. You know, really not the most ideal of conditions, but, you know, we had the cars, we had the U-Haul, we had the heat on, we had music. We were playing some games. We played a little bit of kickball. That was really fun. The scientists were awesome. I got to meet some really, to me, really prestigious people working, you know, with the NSSL, you know, in Norman, Oklahoma. Something that I never thought I'd be able to ever do. So yeah, I mean, now this past summer, I got to work with the data, work with analyzing data and running the WRF with the model simulations. And that was my first experience with running simulations, with running the numerical weather models. And so I'm learning how to parameterize. I'm learning how to, you know, show my results, how to convey relationships, you know, what I'm learning, how accurate the models are. So many different types of, you know, data analysis, you know, what different, radar observations mean. Like, we can get from the Dow what the LMA data means, what this tells us about lightning. And it just keeps on giving. And it's an opportunity that I never thought I'd really be able to get. But I'm grateful that I got it. And I'm grateful to all the people I met, the new friends that I met, and the scientists I met. And I mean, yeah, I think that's everything.
Thank you, Tommy. Very good. That was also really neat, just to sit back and on downtime, the students, and we were interacting with these scientists that are like super published and built and designed these equipment, and the students, I think, learned a lot by those interactions. And then Tommy is one of several students who are. It's a great time to be at SUNY Oswego for meteorology, because we're doing another field project with the eclipse. So some students went down to New Mexico last month for the annular eclipse to launch weather balloons. And then we have the total eclipse coming here in April, right? And we're going to be doing weather experiments with that as well. So, and Tommy is one of several students part of that project. And then we have another field project. I'm not running this one. One of my colleagues, Dr. Wong, Dr. Barber's running the eclipse project, who's at Oswego. Dr. Wong is running this other project where we're sending several students to, I think, Norway. Is that where it is, Tommy? Or where's Dr. Wong sending students to?
I mean, I believe he mentioned somewhere near Norway. Yeah, I think you have it right.
Yeah, to study how clouds form over open bodies, larger bodies of water than Lake Ontario.
Cold air
Right?
outbreaks.
When I was an undergraduate student, I went to class and did homework, played kickball, like intramural kickball. These guys are doing these multi-million-dollar field projects, and I'm in a way, I'm jealous that you guys have these opportunities, and I'm not, in a good way, I'm jealous. It's going to be hard to tell future students, like 5 years, it's not always like this, that we have all these field projects going on at the same time. Because Oswego, it's mainly a teaching school. We don't normally do a lot of research, but some of my colleagues, my young colleagues, they're just firecrackers. They're writing grants and doing this and doing that. I can only write like one grant at a time. I can't do multiple grants at a time. So, are there any other students that'd like to share any stories from the project before we open the floor to questions? Okay.
If you're a student, or if you have a question in general, go ahead, put it in the chat, or just raise your hand and we'll ask your question for you, or we'll let you talk.
I just want to add one more thing. This was my first time. So I'm from Marathon, New York. It's central New York near Cortland. This was my first time actually being in the tug, or being in the Watertown area, and it's pretty awesome. I mean, I love it up there. The amount of snow I seen was incredible, and the people were awesome. The food was great. One of the restaurants we went to after I believe it was an IOP, or setting up the LMAs, taking them down. It was a cool experience there too.
I definitely can't. I just speak highly of how welcoming you all are up here on the Tug Hill, and you love your weather.
Patrick Reynolds, glad you can join us. If you have a question, go ahead and ask it.
I don't know if my mic is on. Can you hear me?
Can hear you loud and clear.
Cool. So I live down on the southern part of the Tug Hill, near Tabor, north of Rome, and I noticed on the plot of your lightning, it was mostly going due east towards Lowville area. Does it also light? I mean, I have seen Lake-Effect lightning down here, but not very often. But does it not really track down here, or is that something else you're measuring?
It can. I don't know if you want to bring up one of the maps, maybe, please. Right there is probably pretty good. Well, at least just a map. Yeah. Yeah, so certainly, I think this is definitely the hot spot, due east of the lake. Even before the turbines went up, right? This is, you get the longest bands form on west-east, because Lake Ontario is oriented west to east, right? So this is your hot spot. But certainly on northwest flow, or west-northwest flow, yeah, definitely you can get lightning in the Rome, Utica area, or just north of Rome, Utica area, west-northwest flow. You can see, I mean, Oswego gets Lake-Effect lightning. I wouldn't say it happens, let's say, every year, or it's a lot less flashes will happen on that west-northwest flow, because it's not taking advantage of the long axis of the lake in terms of all that heat and humidity. And plus, once again, not only do we have turbines, but we're on a hill here, we're on a plateau, right? So that already puts objects into the clouds kind of by having that higher elevation. So yeah, definitely, definitely get lake effect lightning in the Oneida County area. Just not as frequent as to the north. Now this was only for like 1 year during our project. I don't know if you want to go back to one of the other lightning maps. It was toward the beginning of the presentation. I think there was lightning kind of near that area. We can see quickly here. Yeah, maybe one more back, I think it is. Yeah, like you can definitely see there's some lake effect lightning here going into the Oneida County area. Even Syracuse will get lake effect lightning from time to time. But see, Rochester really doesn't get lake effect lightning because for lake effect at Rochester, it has to be like a due northwest wind, and the distance air travels over the water is a lot less to hit Rochester. So I grew up near Rochester, and we get lake effect snow, but once again, this mythical place known as Oswego. The only thing that really made me mad when I came here as a student to SUNY Oswego in the late 90s was that we would get missed all the time. It's not the city of Oswego that gets it. It's Oswego County. It's the Tug Hill part of Oswego County that gets it, right? Or south. There's lake bands like to form along the South Shore of Lake Ontario, and Fulton is kind of like a secondary maximum. So the Tug Hill gets the most, right? Of northern Oswego County, southern Lewis, and the southern Jefferson and Lewis County. But Fulton is the secondary. So it's like Oswego's like a local minimum of snowfall, the city, and that drives my students nuts that we get missed, and because they want to see the snow. And they're like, well, we could go chase it, but chasing it, as Tommy mentioned, it is dangerous. What I asked my students to do, was dangerous to a degree, right? So we had to come up with a document, safety documents, what to do if you get stuck in the snow. Make sure you at least have a half tank of gas in your car, food, water, right? So, we were prepared, right? And there were vehicles that got stuck, right? And luckily, once again, the hospitality of the Tug Hill residents, a truck just came up and pushed us out. I was really grateful for that. So, yes.
Go ahead, Tommy.
Wait. Oh, I'm good to talk.
Yeah.
Yeah. So speaking of getting stuck, on the trip up to CART, we actually got stuck on the off ramp of 81, into Watertown. So that was a very funny and a bit scary moment, because we were trying to get there on time, and it was coming down incredibly hard, and we had multiple people stop by and ask if we needed help. Now, the first person, we obviously said, no, we're going to try to get ourselves out. We could not get ourselves out. So we had a very nice person show us what to do, help, Michael, what do you do with his car, go on the gas, I'll shovel the tire, I'll put a cardboard under it. It was a mission. It was a mission the whole time we were there, but it was fun. It was a little dangerous, but, we knew what to do. We were prepared. We were well prepared. And yeah, so it worked out well.
And students were never alone. It's not like they could drive alone or what have you. They were generally with the scientists or near the scientists. And yeah, the federal government is not going to fund a project unless you have a bunch of safety guidelines and so forth. And but yeah, I felt for my students because here I am in my office. I'm kind of like the coach, right? Directing people where to go, and I'm in my warm office. Mm-hmm. So I felt bad. So there were some events I went out with them, but it was I can't speak highly enough about the undergraduate students and how hard they work.
Another question online. Go ahead, Tom.
Could you talk a little bit more about how grapple and the ice particles have different charges? What's causing that, and how does that affect updrafts and the lightning?
Yeah. So to begin to understand, there's such a thing known as supercooled water, right? Essentially, it's liquid water that exists at temperatures below freezing, right? We're used to water freezing at 32 Fahrenheit because it's touching cold things that are below 32, like puddles on the ground. It's touching cold ground, right? But when you have droplets suspended in air, they don't freeze right away at 32 Fahrenheit. And sometimes it takes it down to, minus 30 Fahrenheit to freeze that water, right? So you get this combination of ice crystals and liquid water droplets, that once those ice crystals touch the liquid water droplet, because the ice crystal's below freezing, right, that liquid water droplet freezes on it. And that's what forms the pellet. That's what forms the grapple. Now, why does grapple get negatively charged? Why do these snowflakes generally get positively charged and then they separate? That's a really difficult question to answer. We for decades, we have these ideas based on laboratory experiments, but we truly are still quite uncertain about how grapple gets more electrons than protons, and why snowflakes get more protons than electrons, like they lose electrons. That's still uncertain. We do know that it depends on the temperature and how much of that supercooled liquid water is in the cloud. Generally, if it's warmer temperatures and more supercooled water in the cloud, like toward the bottom of the cloud, you get more, the grapple charges negatively, right? And the snowflakes charge positively. So we kind of have these measurements that tell us, well, if we have these conditions, we get negative grapple. If we have these conditions, we get positive grapple. But exactly what's going on at the molecular level, you just have to imagine. That's really hard to study. You can't study that really out in a storm, like where we were. You need to do that in a laboratory, right? And there are some ideas that are complicated that I probably would take a lot longer than a couple minutes to explain. But certainly offline, or I can give you my contact information. I can recommend some good books, somewhat high level, or I can explain later. But it really is, it's still a very interesting question about how electrons and it's the electrons that are really moving, how they get charged and transferred between particles. It's really complicated, hard to understand, hard to measure.
Thank you.
Yeah, good question.
Looks like Christine has a question. Christine Stevenson.
Hi, I was just wondering if, I know you said you plan to do another study, but there's been an increase in on the amount of wind farms on the 177 corridor, and there's, more potential for more to come. So I was wondering if you're going to go back and compare if there's been an increase in these lightning strikes and stuff, and what that information would, if that information is going to be looked at.
Certainly. So what we'll be able to compare is if we have two similar storms, let's say the clouds are the same, similar depths, let's say, between what we measured this last winter, and let's say we have a similar storm when we do this next project and it's over the turbines. It'll be interesting to see, is there significantly more lightning? And we definitely will be measuring that, and we can report on that. We are trying, it was someone who had me in touch with at the wind power company. It just fell apart. Like we were emailing, he was going to have me visit from Avangrid, I think, right? Avangrid. And so I'm hoping to share our results with the wind power companies. I mean, this is all public information. I mean, the grant was funded by your tax dollars, right? So this is all going to be publicly available. That website that's on here, you can go on, look for free. You can get the data yourself in a few months. We're processing it right now, making sure it's all quality controlled. But yeah, I want to work with them and kind of help them, if they, because you can actually forecast when these turbines are going to get hit with pretty good accuracy, not to the minute, but let's say tonight, these turbines are likely to get hit. That's useful information. I'm not saying they are going to hit tonight, but if I say tonight, that's useful information for the wind companies, because they could stop the turning of the turbines. Because as it turns out, when they're turning, they're more likely to get hit. So if we could help them in that way, that'd be great. Save money, decrease the chances of lightning happening over someone's farmhouse. I mean, that to me would be very helpful. So I'm hoping to get back in touch with Avangrid and work with them. Yeah.
Anything else online? Anybody in here?
Yep, Patrick had a follow-up question. And
Go ahead, Patrick, and then we'll take the one in.
Yeah, I think he kind of covered it with, I was kind of asking, now that that the lightning, Lake-Effect storms hit lightning or the wind farms, what would be the implication for planning or design of them? I'm sure they're already designed to get hit by lightning, but and you mentioned like turning them up or things like that. Are there other implications that could go broader into how they're used or planned?
That's a great question. That's why I really want to meet with the power company. Is this a problem? I don't even know if this is a serious problem. I
Right.
did hear from someone who's involved with lightning protection for wind turbines that there was a turbine on the Tug Hill recently that was hit by lightning and the blade blew up, right? So there's potential for this to cause damage. Yes, they have lightning arresters. They have lightning like rods on these tips of these turbines and so forth. But the thing about wintertime lightning is it tends to be more powerful lightning than summertime lightning. So if it's more likely to get hit during the winter, these turbines, and the lightning is more powerful, I'm really curious to work with the power company to see how much of a problem is this, and is there a way that we can help them? I mean, maybe that's not a problem. Maybe the lightning arresters do their job most of the time, and the turbines get hit, and there's no problem. But I don't know. It's been very quiet, and since the Owls project in 2010, we've been trying to work with these power companies. And I don't know, the private companies, they might have their reasons for not wanting this to be public. I don't know. But I certainly am very willing to work with the power companies and sharing our data and analysis.
Yes, well, obviously, you found that they've changed since the turbines have gone up. So you're tracking the lightning strikes, but has it changed the intensity or pattern of the storms themselves?
Oh, interesting question.
Can you repeat the question just so they can?
Yeah. So, sorry, what's your name again? Sherry. Sherry's asking, has the wind turbines changed the storms themselves, like where they set up or how heavy the snow is? Like, yeah. Now that's a really good question. I don't, based on like just educated guess, I don't think the turbine fields would actually change where the band's set up. What's really controlling where the band's set up is the wind flow and how the air is interacting with the lake and the shoreline and everything like that. There is a situation during the summer thunderstorms that's been noticed that when lightning happens because charge is separating, but then lightning itself deposits charge in different parts of the cloud. And there's been something known as a phenomenon known as a rain gush in a summertime thunderstorm where lightning happens and then the rain intensity picks up right after the lightning flash because the lightning's changing the charge, and maybe raindrops are getting oppositely charged and they collect and make bigger raindrops, making the rain heavier. Could that be happening in the snowstorms? Possibly. So with these data we collected, we can maybe see if that's happening. But I think it's kind of very short, like within 10 seconds after the lightning flash, maybe the rain rate or snow rate would increase, but not for like a prolonged period of time. I don't know. In science, we never say never. In science, we always talk about supporting hypotheses or rejecting hypotheses. We never say anything's 100% for certain. As much as the media wants to tell you about climate change and this and that and all that, you should never believe anyone who says it's 100% certain. Right? Yes, we're supporting a hypothesis, we're rejecting a hypothesis, and we can make decisions based on supporting or rejecting hypotheses. That's what we're doing with climate change, for example. But I never would say, yes, it's 100% true, or no, that can never happen. So I think it's worth looking into, that question of yours. But I think it would be a minimal impact on snowfall rate and probably a near zero impact on where the bands would set up. But there's so many of these things going up. I don't know.
We have another question online.
Oh.
Go ahead, Jen.
Hi, thanks. This is from Linda Gibbs. Was there an indication of particular turbines generating more lightning due to their elevation or position?
Good question. That's one of the questions we're looking into. Just this summer, our analysis, my students did all this work trying to determine where each lightning flash began. And for one event, we've associated the lightning with a specific turbine. And so it's certainly an analysis we can do and see, is more lightning being initiated by the taller turbines or by turbines that are maybe rotating faster? That's certainly something we can do. Here's the neat thing about turbine lightning I don't think I mentioned earlier. It's upward lightning. So most lightning, the electricity is coming down from the cloud to the ground and then connects to the ground and the electrons flow into the ground. That's what you see as the bright light in lightning. But turbine lightning, it's initiating at the turbine tip and going up into the cloud.
Wow.
The electricity is going up. So could taller turbines initiate more lightning? I don't know, but we can certainly look into that. Certainly if it was downward lightning, I would think the taller it is, the better chance it be to get hit. But since most of this lightning is starting from the turbine tip and going upwards, I don't know if the elevation of the turbine, what effect that would have on lightning frequency. So it's a great question, something we're going to look into. Like I said, certainly be happy to come in another year or so and share with you some of our initial results, and please let me know. I hope I wasn't too technical or whatever. I always tell my students, don't get too technical about terms, right? So, because I mean, if you really understand something, you can explain it to anyone, right? So that's the goal here. Yes.
About precipitation shadow for wind. I thought there was some information out there, data that, and maybe that's more summertime, if there was some kind of that's what they call it, precipitation shadow.
Yeah, well, there's less precipitation downwind of the turbines.
I don't know how far it goes or what that data is.
Well, certainly it could be more the terrain that the turbines are on. Like, let's take the Tug Hill, for example, right? Maybe go to the next slide, please. I think that shows the terrain, right? When air, so let's say air is coming across the lake, hitting the Tug Hill, that air is lifted, right? And that can help to initiate more storms. And then on the downwind side, the air is sinking, and that kind of suppresses storm development. So it could be more of a correlation than a cause and effect, where downwind of this area, yes, there's probably less thunderstorms here during the summer, for example. There's more thunderstorms on the upwind side than the downwind side, but it's probably more because we have terrain and then up and down, not really the turbines doing that. So, but there could be something else going on I'm not aware of with the turbines and how they can change where thunderstorms happen and where rain happens. But I would say that at least with the Tug Hill, I mean, I've seen this a lot where you get heavy thunderstorms, let's say on this side, and then as they cross the Tug Hill, they can kind of weaken a little bit and then reinvigorate in the Adirondacks, right? So, yeah, good questions. Yes. Oh, as it's going up or down? Oh boy. Boy, I don't think we'd have that information. I mean, we can kind of now the power company would work with us. We can definitely relate maybe when the lightning happened, how quickly it was rotating, because I'm sure they have that information. But whether or not it was going up at that time or down, because it's going pretty quickly, I would imagine. That's a good. We could maybe with the power company's data, we might be able to do something with that. Yeah, that's a good question. That'd be neat. Yeah. Yeah. As the blade is going down, you're saying, as the blade is going down, the lightning is going up, maybe. Like that. Yeah. No, that's well, no, but scientifically, it's an interesting question, and it could have broader implications. You never know. I mean, the first time penicillin was found, they didn't think that was going to do anything. Remember, that was a mistake. That was just, penicillin was found as a mistake. It was mold, ew, yuck. But you never know with science. That's the fun thing about science. You never know what you're discovering and the implications it's going to have. Maybe there's a way down the road we can harness this electricity from lightning. That's been an idea for decades. It's so quick, and like Back to the Future, right? It's so quick, and to harness that energy, we haven't been able to figure that out in terms of an economical way, right? So
there's no more questions online.
One more. Tom,
okay.
did you want to get that last one in? Tom wanted to know whether the blades or the nacelles get hit.
The blades of the what?
The nacelles, the central part.
Oh, the hub, like?
Yeah.
I think from the pictures I've seen, some of this work has been done in the Sea of Japan with summer thunderstorms there, and generally it's the turbine tips that get hit, not necessarily the hub. But yeah, I mean, certainly if it's a powering up bolt, or the lightning arresters aren't that effective, I mean, electricity will get into the hub and fry it, I'm sure.
Thank you very much, Scott. This is very interesting.
Oh, thank you. Thank you for coming. Thank you.
We will have this recorded and uploaded onto our YouTube tomorrow, and the presentation available if that's okay online. And so you can get the links and everything that we're being shown. So Really appreciate you taking the time.
My pleasure.
Thank you. Thanks, everybody online.
Yes,
Thank you.
Thank you.
Enjoy the snow this winter. Yeah, no.
Night.
Bye.
It's an El Nino winter, so we should once again get below normal snowfall.